Good morning, madam. Pavitra, ma'am, shall we start?
Yes, Hari, we can start.
Okay. Good morning, all. So, myself, Hari, Assistant Professor, CSC Department. I'm happy to introduce again Mr. Nilagaya Mandal, Consultant, ThoughtWorks, Birhan. So, today he's going to handle the session CA or CD and testing for Unity. Already he handled the session computer graphics, 3D modeling, transformation, and rendering procedure. So now he's going to be handle again CA and CD and testing for Unity. So I welcome you, sir. Now the session is yours.
I think the first session is designing engineering, right? Of engineering of AR/VR applications.
So pardon, sir.
So there are two sessions. The first one is designing engineering applications, right? AR/VR applications.
Yes, sir. Yes, sir.
Okay, cool. So let me share the screen. Yeah. Hope my screen is visible. Hello,
Sir,
hello.
yes, sir. Your screen is visible.
Okay, cool. Okay, so there are actually two sessions. I think there was some miscommunication there, but the first session that we're going to talk about is designing of AR/VR applications. Now, I didn't want to go to the other session because it depends a bit on this. So, thank you everyone for joining in and the organizers for organizing this. And the session we are going to talk about is designing for AR/VR applications. I am Larg Mondal, a consultant at ThoughtWorks. So when it comes to designing for AR/VR applications, there are different things that we need to consider, which are very specific to designing for such application, XR applications in general. And the things that we'll try and cover today are the designing thought process, the way we process like the way we design for a certain problem or a certain issue that we want to cover, the tech designs and the choices, as well as the considerations we need to make when building AR/VR applications, the project planning procedure, how projects are set up and how they are planned for, and finally, the building of AR/VR application, the actual thing. So moving on, the first step in designing for any application is to understand the problem. And it's very vague to just put a description. So let's take it with an example. So let's consider our current situation due to this COVID, that remote collaboration. It's We can take that as the example, and there are certain nuances to collaborating on remote, right? Like team communication, people being far away, people not getting into the right calls at the right time. There is a certain lack of communication amidst the team. Similarly, there are challenges to brainstorming. For example, group discussions where a lot of folks would just sit around a table and discuss and throw around ideas has kind of gone away, has kind of faded away, because you always need to book a time with someone, you need to call someone up via phone, someone has a connection issue, there's a certain amount of gap, right? Similarly, there are less interactions which happen beyond just the work that we do. These all lead into a certain amount of isolation, right? So these are parts of the problems that we are looking into if we take the example of remote collaboration. So once we have a fair understanding of what the problem we are trying to solve, it's always good to have a goal that is set up as to what we are trying to achieve from building an application. So design goals are just your abstract ideas as to what we are trying to achieve as the application we are building. So not to be mixed up with solutions, mainly because solutions are much more concrete approaches to the problems, and design goals are much more of an abstract idea. For example, like building on top of the same example of remote collaboration, maybe our design goals could be about creating a collaborative space somewhere people can work together, or creating an avenue for freely sharing ideas, like whether it's a board on which you can add stickies, or whether it's a place where you can annotate and draw your ideas out, things like that. And relating to your abstract idea of your solution, you need to relate that same idea to your end users. Now, this is very much dependent on the type of users you're going to build. So there are certain questions as a designer that you must, sorry, sorry. So there are certain questions that as a designer you need to ask yourself. The how, like, who are we building it for? Who are the end users? What are their professions? What are their age groups, technical know-how, environment of use, and so on. Professions mainly because how they are going to use the applications, while if it's a school kind of environment where there are students, it's more of a one-way traffic where teacher is delivering a speech to multiple students. That has a very different architecture design than that of a communication where there is a meeting, where there are multiple people trying to talk together. Similarly, the age groups we want to focus on, that will tell you how complex you want your UIs to be, how complex you want your designs to be, whether they're tech savvy or not, whether they're like comfortable working with multiple techs, the environment of use. So there was this one project where we were building an AR application for industry, like people working inside of factories. So where we would normally use things like speech detection to add text to input fields, because it's very hard to do that in head mounted devices. In a factory kind of setting, it becomes very hard. It's always noisy, right? So environment of use, similarly languages and cultures, what things are appropriate where, understanding those lead to a better flushed out design. So moving on, once we are okay with our end users, also the goals we want to achieve, we can go through the different approaches that we can take. This is where we turn our ideas, our goals, to more concrete set of patterns. For example, for remote collaboration itself, there are multiple ways to approach the problem, right? We can go for group messaging, we can go for audio video calls like we are on right now, we can go for collaborative boards like Mural and Trello and all of that. We can also look into other AR/VR based solutions like virtual chat rooms or collaborations in AR spaces. Now, each of these have their own shortcomings and also their own benefits. Like if you just want to broadcast a news or a notification, a chat is better than that of like pulling everyone into a call. Similarly, there are ups and downs of each. So taking those choices is very important. The next thing we need to understand is the kind of experience that we want to give our users. When you're building for AR/VR applications, there are two major factors that come in. One is the complexity of the environment that you're building, and the complexity of the UI or the interface that you're building. For applications like virtual experiences, such as whether it's a roller coaster ride or a 3D tourism, you would have little to no UI and a lot of complicated environments, right? So when it comes to environment, it's mostly about the immersion, the amount of digital content you want to put inside of your in your screen or in your display. To interfaces relate to the amount of control that you want to give your users. So most of the controls that we have are UI based. There are object based controls as well. We'll look into that. But depending on the complexity of environment and interfaces, you have different quadrants of your applications. If you have neither of them, you get reality. If you have a good mix of complex interfaces as well as complex environment, you get something like AR visualization apps, things like customization of automobiles like Hyundai is trying, or something like IKEA's app of putting in furniture inside of your room itself, or even Lenscart, which essentially adds lenses on top of your face. recognizing your facial features. Similarly, you have when you have more intensity of complex environments and complex UIs, you get like data visualization or VR visualization apps, which create complicated structures depending on the data that you're working with. Also, there are VR digital sculpting, which require quite a bit of complex environment and UI. Similarly, you have low environment applications like AR utility apps, which mostly you include 2D applications, but in a 3D context. These are useful mainly inside of head-mounted displays where your entire context is 3D. You rarely get a hand of 2D applications. So even if you need a very 2D-ish application, like that of a settings or a web view, you'd still put it out there in a three-dimensional context so that you can work around. I'm hoping everyone knows the term HMD. It just relates to head-mounted devices. Devices such as your Oculus Go's or your Rifts, your HoloLenses, or your Think Reality A6 devices, things like that, glasses essentially. So once we have our experience understood, once we know what kind of experience we want to give our users, we can scope down the actual problem into bite-sized pieces. The two major bite-sized pieces that are used in the industry are MVPs, that is minimal viable products, and POCs, that are proof of concepts. Now, both of these have their own definition. So, minimum viable product is any product that you can release at the end of your development cycle. Anything that has the minimum basic features, but also is self-sufficient. Whereas POCs or proof of concepts are a bit different in the sense that they aren't meant for any end users, but they are built as prototypes, which are for the mostly for the stakeholders of that project. If you're trying to sell an idea to a certain amount of stakeholders, whether they are like business people or executives, or a different company you want to present an idea to, POCs are used. POCs have a much smaller range or much smaller scope in the sense that all you need to build is something that works. It doesn't have to look good or doesn't have to like meet the end user's requirements, but as long as it fulfills its goal, that is the idea you are trying to present, it is good enough. So looking onto the two examples that we took, that is collaboration in AR and virtual chat room, we can scroll down and like get a basic understanding of the type of features we might want out of, right? So for example, the collaboration in AR, we can think of a collaborative app where people can collaborate on certain boards, right? Where they can add their stickies, add their photos, images, videos, or even paint on top of it. So the basic features would, or the minimum scope would contain something like it should have boards. There should be people who should be able to move around. One can add stickies to the board and visually see other participants. Right. These are the minimum features. Now, of course, it can be extended to a much bigger list. Similarly, when it comes to something like a virtual chat room, there would be people should be in the virtual environment. So everyone should be represented by some kind of representation. Similarly, people should be able to communicate, that is at least audio calls, if not movement. So people should be able to move and look around. So simple actions like looking around or turning their head should be translated to the other users who are viewing them. Similarly, visually see other participants. That is some mock-up or something that represents that the user is there. So this is all about the scoping. Now, before we go into the technicalities, there are two concepts that are very important to understand interactions. That is raycast, which is essentially like using a laser pointer from your device to your environment, to your digital content. What it does, it sends out a ray. Wherever it hits, that becomes your pointer. So in 3D spaces, you really have something like a mouse pointer. So in order to compensate for that, what is used are raycasts. Now there are two ways of using raycast. One is via a controller, another is via gaze. So controllers are pretty simple, as you can see in the image itself. This is kind of a visualization of Oculus Rift, I presume, or Quest, and each of the controller kind of sends out a laser which denotes where your button presses will act upon. We'll go into the technicalities of this later on. Similarly, gaze is something for devices that do not actually have controllers, things like your HoloLens and all. And there you have so in the middle of your viewport, in the middle of your screen, you have a small dot which represents your raycast or your laser as to where it's falling. You can act with different virtual objects and interfaces. So apart from that, there are degrees of freedom. Degrees of freedom represents the amount of movement or amount of control that the user has on the 3D space. So when it comes to 3DOF devices, that is 3 degrees of freedom, they are the simple rotation of your devices. That is the amount of turning, rolling, the amount of yaw or the amount of pitch of the user. When it comes to 6 degrees of freedom, apart from the 3 degrees of rotation, we also have 3 degrees or 3 axes of translation. That is X, Y, and Z axes of translation. These form your degrees of freedom. Now, degrees of freedom, similar to how raycast apply to the HMD as well as the controllers, degrees of freedom also apply to the HMD or the device you're working with as well as the controller. So your controller and your HMDs might have different degrees of freedom. Okay. So now there are certain like standards of building for head-mounted devices and normal AR application. These are the amount of head movement and the amount of field of view that you can present via a device. Normally, it's recommended that from at least the side section, you don't keep your objects beyond a certain range, that is 10 degrees on the negative axis while 20 degrees on the positive. So having a 30-degree field of view when it comes to an up-down rotation. Similarly, on a left-right rotation, 30-degree on either side works fine. Any more than that becomes your peripheral vision. When it comes to side-to-side movements, 15 degrees is a good enough value. Anything beyond that becomes tedious. These are all the head movement calculations or head movement amounts that are the maximum amounts. Similarly, you have field of view. Field of view just determines how much you can see via the device. Now, for certain AR devices, you have a much smaller field of view, which is like pretty small inside of the lenses itself. And they are never as high as 70 degrees or so. They're around 20 degrees or 30 degrees. And you'd have to design specific to what devices you're targeting. But when it comes to virtual devices or VR devices, sorry, is someone speaking? Okay, I guess not. So when it comes to virtual environments, it's always appreciated to have no more than 70 degrees of field of view, mainly because anything beyond that becomes unclear. And also the depth is important. Anything that is beyond 15 meters becomes your background, anything that you don't want your users to focus on, while anything in the mid-range of like 0.5 meters to 15 meters is your actual content. Anything that you want the users to read or visualize or like interact with. Anything that is closer than the 0.5 meters becomes very hard to work with. It becomes too on the nose. So we should always try avoiding that when designing interactions. So moving on to the types of interactions, there are different kinds of devices and interactions along with it. On the AR side of things, you can have mobile AR, which interacts mainly on touch. And this is where you will get the most amount of freedom when it comes to designing UX and UI, mainly because you have a wide area of like touch, like the entire screen is usable. Then you have devices like the HoloLens, which interact without any controller, but mostly based on gestures and your gaze pointers. So this is a classic example of using your gaze pointer to manipulate objects. Now, HoloLens and most AR devices have 6 degrees of freedom, which lets you move around different objects and look at it from different perspectives. Now, there are also devices like the Think Reality or Lenovo's A6 device, which comes with a controller, but the controller has 3 degrees of freedom, while the head-mounted device has 6 degrees of freedom. So the controller essentially inherits some part of translation from the HMD itself. So for those cases, you would normally use the head-mounted device gaze, but use the controller's buttons to manipulate the clicks. When it comes to VR, there are many different types. So mobile VR, which is based off of cardboard or your virtual boxes, are the ones with the least amount of control, mainly because you don't get much in the form of controllers. You can have a Bluetooth controller, but it will have little to no degrees of freedom. So all the pointing would be done from your gaze, which comes directly from your head. You have 3 degrees of freedom based devices like Oculus Go, which gives you no amount of translation, but all rotation. So you can look around, but not move around. But there are ways you can get around this problem. So even in 3 degrees of freedom devices, you can uh, like give a sense of movement. We'll look into how we can do that in the later phases. Also, you have complete 6 degrees of freedom for devices like Oculus Rift and Quest, where you get 6 degrees of freedom both for your devices as well as your controllers. So these are the types of interaction. Depending on which type of interaction we want to work with, we'll design the interfaces as well as the interaction based on these two, like the raycast and the degrees of freedom we get for that devices. So moving on, there are way more different tech considerations as well when it comes to building for AR and VR. The first are the non-functional requirements. These aren't technically related to AR VR, but like every application requires certain amount of these things like security, things like language support. These are not exactly giving you special functionalities, but these are things that you'd have to consider for the app to actually go live. Visibility and orientation of text. This is very specific to AR VR, mainly because depending on how far a text is, the size has to change. So a text which is very visible at around 1 meter distance from the user might not contain the same amount of visibility if it is like let's say 5 meters away from the user. So text visibility is something that is always a challenge when it comes to AR/VR application. Similarly, orientation is. Now, since we are working in a 3D space, you can look at the text from a side angle and it might seem very skewed towards that. So thinking of how you can place objects so that the orientation always faces the back to the user is very important. Similarly, button placement. The head-mounted devices normally have their gaze pointers on the HMD itself, essentially forming a ray from in between your eyes and reaching the virtual content. So any form of cluttering or buttons placed very close to each other becomes very difficult to click. Also, the need for having big buttons is always there because slight movements might shift your gaze and make like essentially cause clicks, unwanted clicks. Similarly, depth management, as you might understand, whenever a ray is being formed, The further away the buttons are, the harder to control the ray. Like little changes in the degrees will have higher changes depending on the day. So it's always applicable to keep the buttons either big or very much closer to the user than other elements. Similarly, you would have integration points when it comes to developing actual applications. For example, the virtual chat, right? It will have third-party applications, like it might connect into Teams or Zoom's APIs to do things like communication over the internet. These are not exactly related to your AR/VR applications, but in general, you will have external systems, APIs, and third-party plugins. So when it comes to immersive experiences, there is also the problem of motion sickness. Long exposures to virtual reality environments can cause motion sickness and simulator sickness to people. So it's always advised to have little to no screen shakes in them, have as little screen shake and movement as possible, and also performance. Whenever you don't have consistent frame rates and have choppy frame rates or performance, it also contributes to the motion sickness. So even if your graphics don't look really high end, that's perfectly fine as long as you have a consistent frame rate holding it. Now, device to device, your performance will vary. You can also have different sliders to control these performances. Experience with less physical movement, yeah, this is something that needs to be considered whenever building AR/VR applications, that you let the user experience the entire thing from one or two specific like positions or directions, not exactly not exactly giving them the need to go around the house, because once you're immersed, it's very easy to get into accidents. So whether you have a table in front of you or something else, those things happen. More later devices like the Quest and all give you an option of building your safe space where all the experience that you get will be inside of that. So such things are always good to consider. Apart from this, device to device and person to person, there are accessibility features you need to think about, like the brightness controls of the devices, like the volume, things like thinking about users who have color blindness, because most of AR/VR applications are based on visualization. Similarly, different people have different focal lenses, so depth of view should be controllable. Also, finally, there's the concept of an uncanny valley. So what the concept is that when you're making something realistic, it comes to a point where in between realism and cartoonic, where the graphics that you design is real enough to not feel like it's a cartoon or animated thing, but not real enough to give you a very unwanted or unsafe kind of a feeling. Those are uncanny valleys. So try avoiding those. Try keeping your graphics much more simpler and comfortable for users rather than going for photorealism, mainly because the performance on AR/VR devices tank quite a bit. And if it's not smooth, it feels very awkward. So that's kind of all the design consideration that needs to be taken care of when planning or designing for AR/VR applications. The other thing that comes after when all the designing part is done is planning for a project. Now, there are many steps when it comes to planning for projects. You start off with the solution scoping, which we discussed before, just understanding how much you want to deliver and how much you want to take a bite out of, not over scoping. It's always okay to underscore and underscope and deliver more than scope high and deliver less. So always keeping that in mind. Then you have feasibility and prototyping. This is the part where if you have some features that you are not very confident about how you want to deliver it, it's always better to have a feasibility check on those things, take some time out of your project building itself and prototype those things out. Once you have a good understanding of what can be achieved, scope them into features, break them down into features. The feature mapping essentially makes sure that you have a good plan of how and at which rate you can deliver a project. Features can be further broken down or sliced down into stories. These are your individual independent tasks or acceptance criteria which can run parallel. This is for slightly bigger teams where you would want to parallelize all the work so that people can deliver faster. And finally, once you have your smallest units ready, you can estimate them to understand the amount of time that you require to build these features and the velocity that your team will take. Once all your velocity calculations are done, you can schedule the stories and create release plans. Finally, you get into the major step of development and asset creation. Now, when it comes to AR/VR applications, you have a separate development cycle, which goes through your picking up of stories, building them, and testing them, and all that. And you have a separate team of asset creators who would like support the development team with the different kinds of 3D models, UI, icons, things like that. So these will normally run parallelly, but the asset creation team would always run a bit ahead in time than the development team. So they normally start a bit ahead. Once your development and asset creation are good, that goes into your testing. Once it runs through all your different types of testings, we'll go through testings in a separate talk itself. You get into the delivery phase. This is where you want to deliver this application to your end user. Whether it's your stakeholders, you just want to put a prototype out there for the stakeholders to try, or you want to launch the application to App Store. So this is the part where you do it. And after every delivery, you might get a certain amount of feedback, and that will help you course correct and go through these phases again to make the next delivery better. So this is kind of an iterative process. This is not a one-time thing. Every time you get a certain amount of feedback, you will course correct and change things around to take the next phase of development. So with that, we kind of complete project planning as well as designing for AR/VR applications. Now let's get into the building of AR/VR apps. So for this, we'll go into a bit of hands-on. So this is Unity, if people are unfamiliar with it. So what I have is a very basic project. It's a Google VR-based project. So I have this basic scene set up here. My VR SDK is set to cardboard. And right now, my project doesn't really have much. It's an empty space. I can look around in this empty space. There is this white box. We'll get into that. There is this collectible object which we can interact with. We can click and it will move to some other place. Okay, and we'll have to find it and all that. So when it comes to AR/VR applications, UI is of multiple types, or should I say canvases on which we display UI are of multiple types. The canvas that we see here, this white box, is a static canvas, is a world static canvas. What it means is that if I have a button inside of it, let's just add a basic button. I'd be able to click this button, but whether I look sideways or move around in the space, this button will remain in the same position with respect to the world. It will not move around or anything. It will be constant. These are called static canvases or static UIs. Static UIs are great when they are with relation to certain objects that you place in the world, but most of the time they kind of get lost. So the other kind of UI is called movable UI, and what we'll do is we'll try building a movable UI. So I'll change this button just slightly. I'll remove. So what I did is I removed the text itself. I'm making it into a square button, and I'll put a certain amount of UI in there, just a move kind of icon, color it so that it's more visible. And we'll try to develop a different kind of canvases or different kind of UI. This will be the movable UI. So in order to do that, what we'll need is a very basic script. You can see the remains of the older one. Okay, so the script we'll add is a drag script. So Unity normally uses C#. So if anyone has any like issues with C# coding, do let me know. I'll go a bit slower. So always it's more or less looks very much like Java, the functions and all the structures. So what we'll try to create here is a very basic drag script, which will have a toggle. So we'll build the API, we'll build a public void toggle drag. This is the function that will be called from the button itself. And in order to move the object, we need the reference of two things. We'll need the reference of the user's camera, their viewport from where they are seeing. So we'll take the transform component of the camera. And we'll also need the object or the canvas we are trying to move. So the object, so to give you a bit of brief about what these are, serialized field just means that I would be able to access that variable from the Unity editor itself, the inspector especially. And transform means the object's rotation, so position, rotation, and the scale of the object. We'll see how we can use them. Also, we need a variable to maintain the state of the object. So we'll take a Boolean variable and call it is dragging or something like that. And by default, the value would be false. And every time someone calls this toggle drag will toggle the value. Once the value is toggled, we need to make sure that the object itself is actually moving. For that, what we'll do is we'll write all of the functionality in this update function. The update function is what is called every frame of your execution. And in every frame, we want the canvas to look directly back at our camera, also be positioned directly in front of the camera, right? So that we get the effect of moving. For that, what we'll do is we'll take the canvas's position and we'll set the position to something of the camera's forward into a certain amount of distance. Right, for now, we don't have the distance variable, but we'll set this up. So distance is how far from the camera you want the canvas to be. Now we can set a constant value, but I will actually set the value here. Whenever someone toggles the drag, I'll set the value up. This is just to make sure that the value does not change when we start moving the camera or the actual canvas. So we'll take the distance, we'll take a pre-built function of vector3, and we'll just calculate the distance between the canvas's position as well as the camera's position. And we get our distance. Finally, we need to add it to our camera's position because it's relative to the camera. So camera position plus the camera's forward into the distance. So I'm not sure. Can we annotate on zoom on this thing? Okay, I don't see any annotate kind of features. It's fine. Okay, so how this acts is that you have your camera's position, which is essentially here. Let me show you where the camera is. So this is our camera. The blue line that you see in front of it is its forward direction. So we take the camera's position, and in the forward direction, we add a vector of a certain distance. That is how it gets placed in the front. So we'll just run this code not yet though. So we'll first have to add this drag script that we just created. And now we need to set up the actual variables. So these are the variables that we set using this serialized fields, the camera and the canvas. Here is where we are setting the values. And finally, we need to call this toggle drag function. That we'll do by the button we just created. So I'm adding it onto the on-click event of the button. Go into drag and toggle drag. So now what we have is a button that will alternate between toggling the drag in and out. So let's see how that happens, whether it works or not. Okay. The update itself. Yeah, update won't occur always. This will occur only if it's dragging. So only if we are dragging, this will happen. Otherwise, it won't. Okay. Yeah. So I can move my head around. Currently, we are not dragging the canvas. The moment I click this, we start dragging this canvas around. Right. So wherever we move, the canvas moves with us. Similarly, I can click again and it will stop dragging. But you can see there is a certain problem with this, right? Whenever I move it to the side, if there is any text on the canvas, it can no longer be viewed. So this is the problem of orientation that we are talking about earlier. So in order to get around this problem, what we need to do is make the canvas we just built look back at us, look back at what, like whoever is controlling it. So in order to do that, apart from moving its position, we'll also set the canvas direction. So the canvas's transform component also has something called a forward. Now we can do the calculations manually, but Unity provides a certain API called lookat. So we'll look at the camera itself, and this will look back at the camera. Now there is a certain problem with Unity's UI, which is that every canvas is actually, so this blue line essentially determines where the forward direction is of a element. Now if this looks back at us, let's say we had a text here, right? We have this new text, and if the canvas was looking back at the camera, which means it would rotate by around 180 degrees, you can see the text gets altered, right? This is because that's how canvases are designed. So in order to get around this problem, apart from making the canvas look at the camera, we'll also have to rotate it by 180 degrees or rotate it backwards. To do that, I will just set the canvas forward to reverse of itself. This in turn will make the canvas look away from us rather than looking at us. So now if we do it, yeah, this is getting blocked by the text. I'll move this text behind. Maybe we can just remove this text for now. Yeah. So now as you can see, if we start moving it, it not only rotates, not only moves around, but also looks back at us as to wherever we leave this. So this is a draggable canvas. So normally whenever we are working with working inside of any HMD, whether it's VR or AR, we'll normally be using canvases like static and movable. But movable canvases are not always applicable. There are also in-betweens, things like soft move camera or auto dragging canvas. So auto dragging canvases are a bit different from the normal canvases in the sense that they don't stick to any position. They are always moving, but they move only slightly depending on where you look. So instead of the camera being instead of this canvas being completely fixed at your center, it will move only when you look away from the canvas. Those are auto dragging canvases. We'll come back to auto dragging canvases if we have time. So similar to how VR works, we can also do the same things for AR. We'll not replicate those, but we'll look at a different project, an AR project this time. So I have a very different setup here. I have a AR session and AR origin. These are essentially part of AR foundation. Yeah. So I have AR foundation and AR core and kit applied to this project. So this essentially makes it into an AR project. And this one would be a mobile AR project. The things that we'll try to cover here are basically, so treat this like it's a simple board in the 3D space. And what we'll try to do is replicate the functionality that we discussed here, collaboration in AR. So for that, what we'll do is try to add different stickies to these boards and try to essentially write to these stickies. Cool. So that's it. So in order to add any sticky to this board, we need a button component or some clickability component on top of this board. I already have a button set up and that has no function as of yet. So we'll write a function to create new stickies and add them to this board. So I'll write a new class called board. Okay. So this one won't need much. So we'll have a add sticky kind of function. I'll keep it public so that it's accessible from the button. So Unity provides a certain feature called prefabs, which essentially means prefabricated objects. These are objects that you have already built inside of your scene and your class, and you can access them and recreate them at runtime to give you different features and different applications. So I have a certain feature prefab already created. It's called a sticky, and this is kind of how it looks. It's a simple image with text field inside of it, input field inside of it. And we'll try to replicate adding these stickies at wherever we click on this board. So we need a reference to this sticky itself. So we'll take the transform reference of this sticky, call it the sticky prefab. And whenever we hit add sticky, we will create a new one. So instantiate is the function that creates new stickies. Now, there are a lot of overloads for this. The one we will go for is the second one, which will also add it in which we will also have to provide its parent, the parent to which this object would be. So we'll take the parent object, which is our holder for the stickies. This will be a sticky holder, and we'll pass the same component here. This becomes our new sticky. For now, we'll just add this and we'll look at the movements after this, or we'll look at the positioning after this. So let's try running this. Okay, I haven't added any scripts, my bad. So I'll have to add the scripts here. Okay, I'll just drag this in. Yeah, so this requires the two components. The holder itself will be our canvas and the sticky prefab. So now we'll also have to reconnect the button. So add sticky is connected. So now whenever we click on this holder itself, we should start getting different prefabs of stickies. Now, as you can see, all of these stickies are actually on top of each other, and they do not actually stick to the place I'm clicking. No matter where I click, all of these stickies are being added at the center. So let's try to fix that. So in order to fix that, what we'll do is we'll try to find the position at where the user is clicking. In order to find that, what we'll use is a raycast. Okay. So we'll do a physics.raycast. This is the raycast we are always talking about, and it requires an origin and a direction. Okay. So for this, we won't use the origin and direction. We'll actually turn our screen point. Let me take the camera component as well. So in order to turn the position of the click into an actual ray, we'll have to take a camera component, the camera from which we are viewing, essentially. Camera.screen to ray, and we'll take the position of our mouse or our touch. That we'll do using input.mouse position. We don't need a max distance, we need an output though. So raycast hit is the class that contains the data once the raycast actually hits any point or any object. Call it the hit. And we'll only perform the actions or add a sticky if this raycast actually hits something. If it does not hit anything, it will not create a new sticky. So once the raycast actually hits a point, we can get the point at which it hits from dot point, and we'll add this as the new sticky's position. So what we are doing here is whenever the function of add sticky is called, we generate a ray depending on the camera's position. We turn the point where we click into a raycast, which essentially hits some point onto this board. Once we understand where the point hits, we'll add that position to the new sticky that we just generated. So if I run this now and I click here, okay, I don't have the camera assigned yet. Yeah, I need the AS session here camera. Yeah, now that the camera is assigned, should work. If I click at the top right corner here, the sticky comes at that point. Similarly, we can add it wherever we want and as many as we want, right? And since these already contain input fields, we can actually add text into this, like new sticky, for example, and it will contain that text. So we can add different stickies and add text on top of that, right? So this is a very simple like implementation of the concept that we are talking about. And wait, let me just check what else I should be covering. Okay, thread of movement. Okay. So as we discussed before, we are going to see how we can use raycast to essentially implement movement inside of a thread of system, right? Inside of a system that doesn't have translation. So in order to do that, what we'll add is a very basic navigation system inside of this VR project. So what we'll do is we have a ground, and on this ground, we'll add a navigation mesh. So these are nav meshes. Nav meshes can be found inside of your AI component navigation. Yeah, inside of your navigation, you can add nav meshes, nav mesh objects. Inside of AI navigation is where you get this toolbar. And this creates a navigation mesh. If you had different objects inside of it, what this would do is create a mesh around these objects. Essentially, let's put it here. You'll also have to turn this object into static. Let's say this object is bigger, right? And if I recreate this navigation mesh, you can see that it crops out that position. What it means is that it will not navigate. So if I had to move from this corner to this corner, it will not go through this object, but around this object. it will avoid any of these white spaces. It will only walk on this blue space. This is a internal navigation system for Unity. And we'll try using this to implement movement inside of a 3DOF system. So for that, we'll add a script inside of this ground class. We'll just call this movement. And this movement class will act similar to a button. So we want a interface called iPointer click handler. And whenever this ground is clicked, what we want to do is take our player. We need a reference to the player. So, and it will be of the type navigation mesh agent. We'll add this component to the player. And depending on where we are clicking, and in order to find the position that we are clicking, we'll also need a reference to the camera. So we'll take the transform of a camera. So here I'm using camera, but for devices like HoloLens and all, you can simply replace this with controller and the same feature would work. So camera dot forward is our forward direction. We'll similarly use another raycast here. So if the raycast hits, and this time we will not get a ray, but we'll have to construct a new ray from the camera position and forward, giving us the direction. And we'll again get a variable out of it of the type raycast hit. This essentially gives us the hit info that we require to find the position where we are hitting. And we need the player position dot destination hit dot position. What this means is that since this is a navigation agent, and whenever we set a destination to it, it will start navigating towards that position. So depending on where we hit the raycast, we'll move the player there. Just to make it a bit more visible, I'll also add a prefab to this. Simple game object called marker. And we'll just put the marker there for visual purposes. Okay, marker dot position dot transform dot position. This is just so that we can visualize where we are making the clicks. Okay, with that out of the way, we'll also create a very basic marker. Okay, give it some material. Okay, and we'll add the script to the ground. So movement script. So we need the camera, the marker itself, and we need to add a nav mesh agent to the player. Now nav mesh agents normally come a bit higher. As you can see, it's a bit higher than the actual base. So if you get something like that, just add a base offset and it will fix itself to the ground. Once that is done, we'll also add the nav mesh agent here. Okay. So once that is done, let's see if the movement happens. So as you can see that it's identifying the ground. Once we click, we are moving there, but we are also kind of rotating our head, right? Since all the rotations are dependent on the VR's SDK, we can actually remove all the angular velocity from the nav mesh agent. what this will internally do is not let the agent rotate around and keep the rotation completely independent of the movement. So let's say we click here and we move to that position. Cool. Okay, this cube will not be static. This will be marker. So we were not seeing the cube because it was marked static. So now if I click there, that's my marker, that's where I'm moving. Right. And we can actually move and grab this. Move too far. I think we can also grab. Okay. Anyways, that's kind of how you implement the movement inside of a 3DOF system. Apart from that, sometimes you might need things like audio cues, like we have this huge box. If you wanted to add audio, you just go for an audio source. And inside of the 3D sound settings is where you will get the amount of like spread of the sound. So spread is where you determine how much of the sound should be spread over your 2 ears. So if object is on your left and you want the sound only to come to your left ear, you would increase the spread. Now spread is normally best at around 0.5 or so, and not higher than that. If it's too high, it becomes very awkward. So that's how you do the spatial audio. So those are the basic things when it comes to covering building AR/VR applications, setting up the different canvases, getting like basic interactions via your mouse clicks and screen touches using raycast. And that's about it. When it comes to navigation aid, building navigation aid is pretty simple. You can add, let's add a very simple navigation aid here. So I'm add this arrow prefab, and we'll add a bit of script into this. A simple look at script. And essentially what this look at will do, it will take a target and not add script. Yeah. Essentially what this look at script will do, it will take a target and always turn itself towards that target. So we'll take the transform of the target and we'll convert its own target or own transform to look at the target object. Over time. So this will simply make it turn towards the other objects. Once the script loads in, let's say we want this board to be the target. So whenever we play this, it turns towards it. Now the actual person can be moving and the arrow will like change its position depending on where you are, whether it's down or up in all 3 dimensions and rotations, it will turn towards the objects. So that is how you might implement a very simple like indoor navigation system and so on in AR. So that pretty much covers the things we're trying to cover. So apart from these few things, there are a lot more enhancements that your applications might need. Things like audiovisual communication. For audiovisual communication, it's always better to use something like WebRTCs, web real-time communication. Then you have real-time syncing. For example, when we are adding the stickies onto a board, the other participants in the same room should be able to see those stickies, right? For things like that, you'd use WebSockets to communicate data across the different participants. Similarly, you have environmental understanding. What we were using a very static kind of field, or I should say relative kind of a field, depending on where you start your application, it will look as if the board is always in front of you. Whether you start looking at east or west, it will always be in front of you. But if you want to change that functionality to something that is more dependent on the environment, you would use something like Cloud Anchors or AWS's Cloud Anchor service to get that feature. If you wanted to put objects on top of things like tables or the floor, similar to how the IKEA app does, you would use plane detection for those. Similarly, if you have multiple people inside of the same room having the same experience, you can replicate animations based on their different movements. For example, if someone is looking or pointing their camera towards a board, you can turn their model to look at the board as well, giving them the illusion that they're in the same space interacting. Similarly, if someone is adding or typing on one of the stickies added to a board, you can give them the animation like they're moving towards the board and towards the sticky, like they're acting as if they're typing. Similar animations you can prompt to give that immersive feeling. So those are kind of the enhancements we can look into. So that's about it from my side. If we have questions, love to take them. Any questions?
Thank you, sir. Participants, if you have any queries, kindly unmute yourself and interact with the resource person. Participants, if you have any queries, kindly interact with the resource person.
Okay, if there aren't many questions, let me share one more time. Since we already built an AR application, let's try deploying this AR application to an actual device. Okay. Some connection issues. If anyone has any questions, feel free to call out. Yeah, now it's connected.
Participants, if you have no more queries, then we can conclude. If you have any queries, kindly unmute yourself and interact with the resource person. Participants, if there are no more queries, Then we shall conclude. Thank you, sir. Thank you for the wonderful session.
Sure.
It was really useful and highly informative. I hope this will benefit all the participants to do more innovative works in Unity. Thank you so much, sir.
Sure. My
Participants, you
pleasure.
can leave now and join by 12 o'clock. Thank you all.
Thank you.